All right, here's an example problem. We have a planet that's in orbit around a star. All right, so this is nothing to do with our solar system. This is just some planet around some star. The distance from the star to the planet is 450 million kilometers. All right, so that's an important number. Let's write that down. All right, so the distance is 450 450 million kilometers. All right, so that's going to be million is times 10 to the sixth kilometers. All right, so we'll return to that in just a second. The time it takes for the planet to orbit once is measured to be 3.2 years. Find the mass of the planet. Let's see. Find the mass of this sorry. Find the mass of this star. Um, uh, a planet orbits this. It does that sometimes. I didn't notice that. All right, yeah, it's just repeating the question. I didn't mean for that to happen. Anyhow, that's why it looks confusing to me. So we know the period, right? So the period is 3.2 years, and we want to find the mass of the planet, right? That's the key thing is we got to find the mass of the planet. All right, so let's write down the period. I'm going to write it down here because we're going to do a little conversion in just a moment. The period is 3.2 years. All right. So to find the mass, right? And remember, that's what we're looking at. We're going to use what's called the modified version of Kepler's third law. I mean, immediately we know that this is not a Kepler's, the original Kepler's third law, where a cubed is equal to p squared. I mean, that's certainly true, but not in this situation, right? That is only true for something that's orbiting our sun. All right. So this is a general problem, and so we write down the modified. Anytime you're looking for mass, right? If it says what's the mass of the star, we're using the modified version, right? So this is 4 pi squared, the distance cubed. Oops, cubed. Sorry, divided by big G, divided by the period squared. Period squared. All right, so there's a couple of things about this one that we have to realize. The distance d has to be in meters. All right, so we're going to convert this one to meters, and then the period has to always be in seconds. All right. Big G is what it always is. Remember, big G is 6.67 times 10 to the minus 11th. I mean, big G actually has units, but as long as you have the units of the distance in meters and the period in seconds, you're good to go. All right, so let's convert this right away. We know that in 1 kilometer, there are 1,000 meters. Or I'm going to write 1,000 like this: 10 to the third meters. All right, so the kilometer part cancels, and so that changes this to 450. So times 10 to the sixth times 10 to the third, you just add the exponents, right? So this is going to be 450 times 10 to the ninth meters. All right, so we're going to put that in our pocket for a minute. That's 10 to the ninth. It doesn't really look like a 9. It actually looks more like a 4. Sorry about that. Let me erase that. Sorry. Don't want anybody to get the wrong idea. All right, so that's 10 to the ninth. There, that looks better. All right, so the other thing, of course, is the period, right? So the period's given to us in years, so we have to convert that to seconds. I'm pointing at the wrong thing. That's big G. All right, and then of course we're going to use the modified version of Kepler's third law. All right, so here we go. So in 1 year, there are 365.24 days. All right, so the years cancel, but that's fine. It converts us into days. That's not what we want. We want to convert this all the way down to seconds. So we know that in 1 day, there are, of course, 24 hours. I'll use an H for hours. The days cancel. And then, of course, we know that in 1 hour, we're putting 1 hour in the denominator, and we know, of course, that that is 60 minutes. And remember, use MIN for minutes, because we don't want to we always want to leave lowercase m by itself, reserved for meters. All right, and then the last thing is, of course, 1 minute. 1 minute is 60 seconds. That's supposed to be an S. Sorry. So the minutes cancel. All right. So this is really literally all we have to do is we multiply. Here, I'm going to do this now. Let's get our. See if I can find my calculator here. There it is. All right. So we're going to multiply 3.2. All right. So 3.2 times 365.24 times 24, and then times 60. It's times 60 times 60, or you could just say times 60 squared. All right, and that is the answer. Okay, so that's the number of seconds. And let me move this over just a little bit. So that's what we're going to put in for p. Remember, this p is squared. It doesn't really look like a 2. All right, so that's the p has to be squared. All right, so I know that. I know the p is going to be squared. So let's go ahead and square it. All right, so that's the it's over. It's 100 million seconds. All right, that's what 3.2 years is. All right, so I'm going to square it because I know I'm going to need that a little bit later. All right, so squared. All right, so now the other thing that you can do with these scientific calculators is you can store this, right? It's always good to be able to store things. So I'm going to let's see, memory storage. So let's store that. All right, here, let me clear it so that's this big huge number. That's the number of seconds squared. So if I clear that and hit this memory recall, there it is. All right, so when I do the calculation, I'll be able to use that in just a few minutes. All right, so the other thing we already converted the distance, right? The distance is 450 times 10 to the 9th, which is billion, by the way, 450 billion meters. So what I'm going to say, 4 pi, all right? So, 4 pi squared, all right? So we got 4 times pi squared times, all right, so I'm going to put this 450 times 10. So you got to use the EXP button or the EE button if you have a Texas Instrument. Anyhow, times 10 to the 9th. And of course, you see in Kepler's, the modified version, remember, it's Isaac Newton who modified this for us. We still have the distance cubed and the period squared, but what that does, this universal formula allows us to figure out the masses. Mass when one object is orbiting another. That's the whole purpose of this. Anyhow, now I have to cube that. All right, so let's see. So if I hit this x to the y button, all right, so x to the y button, raised to the third power, raised to the third. All right, so I've just done the entire numerator, and I've got to divide by big G. Okay, so divided by, and so big G is 6.67 times 10 to the minus 11th. 10 to the, make sure you're using the negative sign, negative 11th. All right. And now that this is not the final answer, I still have to divide by the period squared. So I hit equals, and then I divide it by, remember, I put that in my storage. All right. So I'm dividing by the memory recall, and then I hit enter, or equals. All right. And so that is, yeah, this is not in scientific notation. Hold on. Let me change that to scientific notation. All right, so the decimal point is way back here. Here's what I'm going to do, right? This is kind of convenient because you got every 3 digits there's a comma. So if I go in sets of 3s, right there's 3, right? So that's 10 to the 9th, 3 more. That's 10 to the 18th, and then I go 3 more. That's oops, let me go. I miscounted. So 3, 1, 2, 3, and then 3. Let's see. Oh, jeez. So anyhow, so here's if you I know that it's going to be 5.3 times 10 to the 30th. Okay, so look, if I take this number and let's say if I divide by 1 times 10 to the 30th, I should get 5.28. All right, so if I do, so this is just to make sure that I have that this number is indeed 5.28 times 10 to the 30th. All right, so divide it by 1 times 10 to the 30th. All right, and that gives me so that 1 times 10 to the 30th is that's really going to be my scientific notation. I'm going to round this to one place past the decimal. So it's going to be 5.28. So I'm going to round up. So the 2 becomes a 3. So the answer is going to be 5.3. And see, remember I divided by 1 times 10 to the 30th. So it's going to be 5.3 times 10 to the 30th. I mean, this particular calculator is kind of a pain because it's not really showing you, and it's not a lot of fun to count the decimal points. All right, so this was. Hang on, let's go back to this. All right, so this is the answer to this. So once we plugged everything into the modified version of Kepler's third law, this becomes 5.3. I mean, there's lots and lots of digits after this. But see, the thing is, in astronomy, knowing these first 2 digits is more than sufficient. Times 10 to the 30th kilograms. All right, so that is our mass rounded one place past the decimal. All right, so that's how you do it. Just for a comparison, so this is going to be more massive than our sun, right? Our sun is here. Let me write this down. This is just a side, okay? We've solved the problem, right? This is the answer. But if we were to compare it to the sun, the mass of our sun is 2 times 10 to the 30th. And so if we were to compare the two, it turns out that, of course, the mass of this star is 2.65 times the mass of the sun. You just divide this number by this number. always divide by